Hello everybody. In this lesson, we will talk about random forest for our project. And in the previous part, we repeat same steps, and I will pass and I will start from the directly random forest part. And let me switch. Again, we have a baseline model for linear regression, and here we have a random forest regressors. And what happens here, and let's begin from that. In this part of code, we initialize random forest regressors with 100 trees, and the max features squared here. It parameter means that each tree will consider the square root of the total number of features when looking for the best split, and the random state 42 ensures reproducibility by setting a seed for the random number generator. When we fit the model to our training data and clip the target variable, and what we can say, let's look at the y-head train part with RF predict. What happens here? And here evaluate y-train clipped, y-head train and train. Here we use the trained random forest model to make predictions on the training data, and the predicted values are stored in y-head train. When we then evaluate the model's performance on training data using the evaluate function, which calculates the root mean squared error and R squared score and prints them out. And here you can see the output values here. The output indicates that the model performs very well on the training data with a low RMSE approximately 5.92 and a high R2 score of 0.98, and it's good. And let's look at this part, y-head test and evaluate. We make predictions on the test data and store the results in y-head test, and we then evaluate the model's performance on the test data using the evaluate function. And here you can see the test set values. The output shows that the model's performance on the test data is not as good as on training data with an RMSE of approximately 29, and R squared is 0.74. And what we can say, this indicates that the model is overfitting the training data as the performance significantly drops when applied to new unseen data. And let's look at this part, what happens here. We will check the overfitting, and in this part we check the complexity of a single tree within the random forest. We print the maximum depth of the tree, which indicates the number of nodes along the longest path from the root to a leaf. And we also check the number of samples in the leaf nodes, which shows how many samples each leaf node contains. And 33 and array, what are they? The output shows that the tree has maximum depth of 33, which is quite deep. And the array indicates the number of samples in each code, and the presence of nodes with very few samples suggests that the tree is making very specific splits, which contributes to overfitting. And let's switch and let's look at the another parts. Okay, so let's look at this part. What happens here? In this part of code, we initialize random forest regressors with 100 trees, considering the square root of the total number of features for each split and random state, you can see. And we set max depth equal 8 to limit the maximum depth of each tree, and bin samples leave 50. Okay, to ensure that each leaf node contains at least 50 samples. and these parameters help in reducing overfitting. We then fit the model to our training data and the clipped target variable. And what we can say again, predict and evaluate part with this. And we use the trained random forest model to make predictions on the training data. The predicted values are stored in y-hat train, and we then evaluate the model's performance on training data using the evaluate function, which calculates the root mean squared error and r squared score and prints them out. So here the values, what we can say for train. The output indicates that the model performs reasonably well on training data with an RMSE approximately 15 and R squared score of 0.85. And same parts for test sets. And let's look at the test values here. Output shows that the model's performance on the test data has improved compared to the initial random forest model. And now RMSE approximately 20, we can say that 21, and R squared score is 0.74. And this indicates a slightly improvement and reduced overfitting compared to the previous model, where the test RMSE was 21.05. And let's look at these parts. Here we will visualize our decision trees, forest, and it is a long visual. And let me switch. We can say sorry, it is long, and okay, it is on. What we can say about these pictures or visuals. The provided image displays one of the decision trees from our random forest model, and each node in the tree represents a decision based on the feature. And the tree splits the data at each node based on specific conditions, ultimately leading to leaf nodes that provide the predicted remaining useful life. And each node contains the following information: the feature and threshold used, split, and the mean squared error, and the number of samples reaching that node, and the predicted value of rule for that node. And how about the colors? The colors of the boxes represents the predicted remaining useful life values, and with darker colors indicating higher values, and lighter colors indicating lower values. And this color gradient helps to visually differentiate nodes based on their predicted remaining useful life. And what we can say, some nodes in the tree result in very inaccurate predictions indicated by a high MSE value, and this suggests that the splits made at these nodes do not effectively reduce the prediction error. And what we can say, sensors 9 and 14 frequently appear as splitting criteria in this tree. However, these sensors were previously identified as not being very effective in distinguishing between fault modes. And this observation suggests that using these sensors might contribute to higher MSE values and less accurate predictions. And what we can say here, based on the insights from the tree visualization, the next step is to refit the random forest model without using sensors 9 and 15. And by excluding these sensors, we aim to see if the model's performance improves. And I think it's okay. And let's look at these parts and what happens here. Sorry. Okay, it's okay now. Again, dropping sensors and clipped parts, and you can see the X train and Y train parts. Let's look. First, drop sensors. In this part of code, we specify which sensors to drop based on their poor performance or redundancy, and the sensors 1, 5, 9, 14, 16, 18, and 19 are excluded from the training dataset. We then combine these with index and setting names to create the drop labels list, and the remaining sensor list contains names of the sensors we will retain for the model training. And X train, Y train, Y train clipped. What happens here? We create the training dataset X train by dropping the columns specified in drop labels. We then separate the target variable remaining useful life from X train and clip its values at an upper limit of 125 to avoid overly large values. And here X test. For the test dataset X test, we ensure that we use only the last record for each unit to represent the test set. And we drop the same columns as in a training set for consistency. And let me switch here. Let's look at this part. In this part, we reinitialize the random force regressors with the same parameters as before, and estimators using 100 trees in the forest and max features squared, considering the square root of the total number of features for each split. At random state, max step equal 8, limiting the depth of each tree, and minimum samples leaf, ensuring each leaf node contains at least 50 samples. And here evaluation part. And let's look at the train and test RMSE values. The output shows that the model's performance on the training data has worsened slightly, with an RMSE of approximately 17.60, and our Sukar score is 0.81. And for test values, what we can say, output indicates that the model's performance on the test data has also worsened, and you can see data. So what we can say, dropping sensors 9 and 14, the model's performance worsened both on the training and test datasets. Therefore, despite their mediocre performance, sensor 9 and 14 are kept in the model as their exclusion leads to a significant drop in performance. And I hope that part is okay. And let's look at this parts and smooth. We will talk about the smooth. And what happens here? We have a function here. The smooth function is defined to apply smoothing to the sensor data, and smoothing helps to reduce noise and make it easier to distinguish between different fault modes. And DF sensors and DF group by unit sensors. What happens here? For each sensor, we calculate the rolling mean over a specified number of samples, and this operation is performed for each unit individually. And here we have another function, and its name create masks. What happens here? Let me select like that. Okay. The create mask function generates masks to drop the initial non-values introduced by the rolling mean calculation. The mask ensures that only valid data points are retained. And their columns, smooth sensors, and return last part here. After smoothing, the sensor columns are renamed to indicate that they have been smoothed. The function returns the smoothed data frame and the list of smoothed sensor names. And I hope it's okay. And let me switch slightly. Okay, let's stop here. And what happens here? First, train smooth equal train copy. What does it mean? We create a copy of the original training data to work with, ensuring that any changes we make do not affect the original dataset. And here dropping part, we drop the columns specified in drop sensors and setting names from the train underscore smooth dataset. This step removes the columns we deemed less useful or redundant from our previous analysis. And here smooth function and train smooth and 15. Now that part, we apply the smooth function to the train smooth dataset using the remaining sensors list, and the function calculates the rolling mean over 15 samples for each sensor, smooths the data, and returns the smoothed data frame along with the names of the smoothed sensors. And here, let's look at this line. This line of code calls the plot signal function to visualize the smoothed data for sensor 7. And the plot signal function generates a plot of the smoothed sensor values against the remaining useful life. And what we can say here, let's talk. The output plot shows the smoothed values of sensor 7. You know that, and each line represents the smoothed sensor values for a different engine unit, with x-axis representing the remaining useful life and the y-axis representing the smoothed sensor values, like that. And the lines exhibit smoother trends compared to raw sensor data, and making it easier to identify patterns and changes in sensor values as the remaining useful life decreases. And smoothing helps in reducing noise and highlighting the underlying trends in the data, which can improve the model's ability to distinguish between different fault modes. And what we can say, smoothed data for the training set looks good, and meaning the smoothing process has effectively reduced noise and highlighted meaningful trends in the sensor data. And the next step is to apply the same smoothing process to the test set, retrain the model using the smoothed data, and evaluate its performance. And here, same part, as you can see here, for test data. And I will pass, and let's look at our outputs and talk about them. What we can say here, despite applying the smoothing process to both the training and test data, the root mean squared error on the test set did not improve compared to the non-smooth data. And this indicates that the smoothing the sensor data did not enhance the model's ability to predict the remaining useful life in these specific instances. And what we can say here, let's look at these parts, and we'll look at the hyperparameter parts, and let's talk. Again, we create a random forest regressors instance with these parameters. Again, you know that parameters, and we fit the model to our training data, and we then predict and evaluate the model's performance on the training and test sets. And you can see the values. What we can say, it's okay. And let's look at the rf.get params. This function call returns a dictionary of all the hyperparameters of the random forest regressors, and the output lists parameters such as bootstrap, CCP alpha, criterion, max depth, max features, in samples, leaf, and unestimators, and many others. And by analyzing these parameters, we can decide which ones to adjust in our hyperparameter tuning process to potentially enhance the model's performance. And what we can say else, let's look. When we training random forest models, one of the main difficulties is managing our fitting while aiming for optimal performance. And the following parameters can help in mitigating our fitting and enhancing the model's overall effectiveness. And first, max depth here. This controls the maximum depth of each tree, and mean samples leaf. Where is it? Okay, here. This sets the minimum number of samples required at each leaf node. And CCP alpha, what is this? This is a cost complexity parameter that prunes leaves post-fitting, affecting the tree's maximum depth, and mean impurity decrease. Here, let me select OK. This specifies the minimum decrease in impurity that must be achieved for a split to occur. And while max depth and mean sample sleeve are fairly straightforward, CCF alpha and mean impurity decrease require more detailed consideration. And the CCP alpha parameter, standing for cost complexity pruning, helps in calculating an alpha value that signifies the complexity of the decision path from the root to the other nodes. And lower alpha values suggest higher complexity. And by pruning nodes with alpha values below certain threshold, you effectively trim the tree of our fit nodes. And we will explore appropriate thresholds for alpha in the subsequent steps. And let's look at these parts. What happens here? Okay, let's stop here. This section of code is focused on the analyzing the cost complexity pruning path for the random forest model. And let's look at first path RF dot estimators and to impurities. And let's look at these two lines. What happens here? The cost complexity pruning path method calculates the effective alpha values and the corresponding total impurities of the leaves for each split in the tree. And this is done for the fact estimator in the random forest. And here you can see the plot codes. A plot is created to visualize the relationship between the effective alpha values and total impurity of the leaves, and x-axis represents the effective alpha values and y-axis represents the total impurity of the leaves. And the plot helps in understanding how pruning affects impurity in the decision tree leaves. And let's look at our plot. What we can say. At very low alpha values, the total impurity increases rapidly, and this indicates that the initial splits in the tree significantly reduce the impurity. And plateau region, as the alpha values increase, the rate of increase in impurity slows down and the curve enters the plateau region. And in this region, further pruning has a less dramatic impact on impurity, suggesting that the tree has reached a point where most splits are adding marginal improvements to purity of the leaves. And let's look at this part. At higher alpha values, there are sharp jumps in the impurity, and these jumps occur when entire subtrees are pruned, indicating that the tree is becoming simpler by removing sections that contribute less to reducing impurity. And a lower alpha value will result in a more complex model with lower impurity, while a higher alpha value will result in a simpler model with higher impurity. And finding the right balance is important for optimizing model performance and avoiding overfitting. And I think it's okay. Let me switch another part. What happens here? Again. So the plot is created to visualize the relationship between effective alpha values visualize the relationship between effective alpha values and the total impurity of the leaves, but this time it's zoomed in. And the x-axis represents the total impurity of the leaves, and by excluding the last 10 values from the CCP alphas and impurities, the plot zooms in on the lower range of effective alpha values, providing a more detailed view of how pruning affects impurity in this range. And what we can say here. First, lower values. At very low alpha values, the total impurity increases more gradually, and this detailed view highlights the smaller steps and finer changes in impurity, which are not as visible in the broader plot. And the zoomed-in plot allows us to observe incremental changes in impurity more clearly. Small increases in effective alpha result in more discernible changes in impurity, making it easier to understand the impact of each split. And even in this detailed view, sharper jumps and plateaus can still be seen, indicating significant pruning events that reduce the complexity of the tree. And what we can say, for effective alpha values below 2, the cost complexity is highest, but this also results in a significant reduction in leaf impurity by approximately 50 points, which equates to about 7 in terrain RMSE. And this range appears to be optimal for hyperparameter tuning. So the impurity decrease metric measures how much the error reduces after a split, taking into account the number of samples in both the parent and child nodes. And if the impurity decrease is lower than the specified threshold, the split is reversed. And we will explore appropriate values for the minimum impurity decrease parameter to improve model performance. And let's look at these parts. What happens here? In this snippet, we are using the help function. Okay, here help from Python to get detailed information about the tree class from the scikit-learn tree and tree module. And this class represents a binary decision tree, and the help output provides us with detailed documentation on its attributes and methods. And what we can say, the help documentation explains that the tree class is an array-based representation of a binary decision tree, and each element in the arrays holds the information about the nodes, where the node at index 0 is the root of the tree. And what we can say, node count, the total number of nodes in the tree, and capacity, the size of the arrays that represents the tree, which is at least as large as node count. And here, max depth, the maximum depth of the tree, and children in left, an array indicating the left child of each node. And I hope it's okay. And let's look at these parts. Here, we are extracting various attributes of decision tree from a random forest estimator and organizing them into a dictionary. We then convert this dictionary into a pandas data frame for easier manipulation and analysis, like that. And here, ID node, what is this? The unique identifier for each node in the tree, and impurity, second line, the impurity measure at each node, and impurity indicates how mixed the classes are in the node, and lower impurity means more homogeneity. And samples here, the number of samples reaching each node, and this gives an idea of the data distribution across the tree. And ID left child, what is this? The node ID of the left child, and if value is -1, it means the node is a leaf node and has no children. And ID right child here, the node ID of the right child, and similar to left child, -1 indicates a leaf node. And let's look at our table and what happens here. For example, ID node 0 and impurity value samples ID left child and ID right child. This is the root node with the highest impurity and the total number of samples. And node 1, second line, this node has split from the root node, reducing impurity significantly. And node 2, further splitting has reduced impurity. and 3, 4, 5, 6, 7. What we can say, input is decreasing values indicate progressive refinement of data purity, and for samples decreasing as we go deeper, showing fewer samples reaching these nodes, and children valid child node IDC indicate continued splits, and 8 and 9 impurities were low indicating high purity, and samples very few samples, and here -1 for both children indicating these are leaf nodes, and this table shows how the decision tree is structured, how impurity decreases as we move from the root to the leaves, and how the number of samples reduces, indicating that the tree is effectively splitting the data to achieve higher purity at the leaf nodes. And this information is important for understanding the decision-making processes of the tree and further tuning and optimization. And let's look at this part and what happens here. Let me see which one. Okay, here these two lines are checking if all leaf nodes have a value of -1 for both ID left child and ID right child, for confirming they don't have any children. And how about the output here? The output array confirms that leaf nodes do have -1 as their child node values. And here initialize and calculate impurity decrease part. And what happens here? Let's talk. Impurity df and equal np none. It initializes a new column impurity decrease in impurity df with none values, and samples total. Here it stores the total number of nodes in the decision tree, and we have a for loop here. What happens here? It starts a loop from the second node, I mean index 1, and because the root node, I mean index 0, doesn't have any splits prior to it. And let's look at the if part. Let's select, sorry, okay. What happens here? If the node is a leaf node, it skips the calculation since leaf nodes don't split further. And in the else part, impurity p samples p, what does mean? Let me select, I think it's okay here. It extracts impurity and sample count of the parent node, and IDL and IDR, what is this? It is the left and right child node indices, and here impurity L and samples L extracts the impurity and sample count for the left, and impurity R samples R, it extracts the impurity and sample count for the right child, and I think it's okay. So we can switch, and what happens here? This code snippet is used to display the top rows of the impurity df data frame and to plot the distribution of the impurity decrease values like that. And what we can say, let's look at the output first. ID node, the index of each node in the decision tree, and impurity, the impurity value at each node, samples, the number of samples that reach node, and that part, and impurity decrease. The decrease in impurity achieved by splitting the node into left and right children, and the root node, I mean ID node 0 here, has the highest impurity and most samples. And as we move down the tree, the impurity generally decreases and the sample size at each node also decreases. And nodes with ID left child and ID right child values of -1 are leaf nodes and thus don't have any impurity decreases value. And here we have a histogram output, what we can see here, the histogram shows the frequency distribution of the input decrease values across all nodes in the decision tree, and the majority of nodes have a relatively low impurity decrease, with a few nodes having very high impurity decrease values. And this distribution indicates that while most splits provide a small reduction in impurity, a few key splits contribute significantly to improving the mod's performance. And let's look at these parts. Again, impurity decrease, and what happens here, what we can say here, increase. This line provides summary statistics of the impurity decrease column, including count, mean, standard deviation, minimum quartiles, and maximum values. And count, there are 112 nodes with calculated impurity decreases, and mean, the average impurity decrease is approximately 282.52, and the standard deviation is 994, indicating a wide range of impurity decrease values. And the minimum impurity decrease is slightly negative, which might be due to rounding for computational errors. And quartiles, you can see, and max values, and I think it's okay. And let's look at these parts, what happens here. This line filters the impurity DF data frame to only include nodes with impurity decreases less than the 25th percentile, and it is 14.59. It then plots a histogram of these impurity decreases. So what we can say for this histogram? The histogram shows the frequency distribution of the smaller impurity decreases, and the distribution indicates a range of smaller impurity decreases with median values close to the lower bound. And this histogram can help identify thresholds after, for pruning or further model refinements. And let's look at these parts. Grid search for hyperparameter tuning. And here, these lines import random search CV for performing the randomized grid search, and group key fold for cross validation. And here, max step, a list containing none and range of values from 3 to 33 incremented by 3. And this parameter controls the maximum depth of the tree. And mean sample sleeve, a list of values from 1 to 101 incremented by 10. This parameter defines the minimum number of samples required at a leaf node. And minimum impurity decrease, a list of values from 0 to 14.6 incremented by 0.1, and this parameter specifies the minimum decrease in impurity required for a split. And CCP alpha, a list of 81 evenly spaced values between 0 and 2, rounded to 3 decimal places. And this parameter controls complexity cast pruning alpha, which is used to prune leaves after fitting. And here, parameters, this dictionary consolidates the lists of hyperparameters defined above. Each key corresponds to a hyperparameter name, and each value is the list of possible values to be tested. And I hope it's okay. And let me switch. What happens here? Tuning options. Here, this code calculates the total number of possible hyperparameter combinations that will be evaluated during the randomized search. And length max depth here, and what happens here? This compute the number of elements in each hyperparameter list, and the product of these lengths gives the total number of combinations, and the print tuning options statement outputs this total number, which is really big value in this case, indicating a very large search space. And let's look at this part, iterations and another parts. What happens here, what we can say, this section of code sets up and executes the randomized grid search for hyperparameter tuning of the random forest requesters, and iterations specifies the number of iterations for the randomized search, and this means the search will randomly select 30 combinations of hyperparameters from the total search space. And RF, it initializes a random forest requesters with 100 trees, the square root of the number of features for the best split, and a fixed random state for reproducibility. And GKF, what is this? Defines a group k-fold across validator with 3 splits, and this ensures that the same unit is not present in both the training and validation sets during cross-validation. And requesters, let me switch. It configures the randomized search CV with the following parameters. RF, by the way, let's look at this first. Okay, sorry. Okay, RF, the random forest model to be tuned, and parameters, the hyperparameter grid defined earlier, and CV equal GKF uses the group k-fold object to perform cross-validation, and iterations limits the number of hyperparameter combinations to the test to 300, and njobs -2 utilizes all available CPU cores for parallel processing, and scoring, what we can say for that, uses negative root mean squared error as the scoring matrix, and I think it's okay. And let me switch, and what happens here, and let's talk. Let's stop. Results, here it converts the cross-validation results from the randomized search CV object into a data frame, and columns specifies the columns to include in the data frame for display, and results here columns dot sort values. It sorts the data frame by the mean test score in descending order to highlight the best performing parameter combinations. And we have a table here. The best performing parameter combination has per mean samples equal 1, and like that, and the second base combination has per mean samples leaf equal 21, and per mean impurity decrease 0.6, and per max depth 18, and per CCP alpha 0.975, and another scores. And here worst performance, the lowest performing combination has per mean samples leaf equal 1, and per mean impurity decrease, how is it, 13.9, and another values. So what we can say here, we can say that the results obtained from the randomized search are not reproducible, and this means that restarting the kernel and rerunning the notebook may yield different results, and this issue can arise due to several factors, including random initialization in the model training process and changes in data loading or pre-processing steps. And I think it's okay. And what happens here, the print requires the best params and requires best score. It outputs the best hyperparameters found during the grid search and outputs the best score achieved with those hyperparameters. And what we can say here, we build our final model training and evaluation. You know that parts, and let's look at the outputs here. Train and test RMSE values. What we can say, the test RMSE is compared to the baseline model's RMSE to calculate the percentage improvement, and this indicates 7.65% improvement in the test RMSE over the baseline. And I think it's okay. It is a very long lesson. Thank you so much for your listening and attention. See you in the next lesson.